This video demonstrates the spruing, investing, and casting procedures for metal framework removable partial dentures. The purpose of a sprue former is to provide a channel through which molten alloy can reach the mold in an invested ring after wax has been eliminated. With large restorations or prostheses, such as removable partial denture frameworks, the sprue former are made of wax. High-heat chrome-cobalt alloys are cast using a sprue that approaches from above and gives rise to a number of smaller accessory sprues. Care must be taken to round all the sprue connections. Sharp edges in the refractory material can be broken off as molten alloy enters the mold. These displaced fragments can be carried deep within the mold and may ruin the casting. The sprue former is attached to the wax pattern with a pattern on the refractory cast. Select a sprue former with a diameter that's approximately the same size as the thickest area of the wax pattern. If the pattern is small, the sprue former must also be small, because attaching a large sprue former to a thin, delicate pattern could cause distortion. On the other hand, if the sprue former's diameter is too small, this area will solidify before the casting itself, and localized shrinkage porosity or suckback porosity may develop. The ideal area for the sprue former is the point of greatest bulk in the pattern to avoid distorting thin areas of wax during attachment to the pattern and permit complete flow of the alloy into the mold cavity. Any area that is separated from the bulk of the framework by a long span of lattice work or meshwork requires a secondary sprue former. These secondary sprue formers should be 1/3 to 1/4 of the diameter of the main sprue former and should be gently curved. A reservoir should be added to the sprue network to prevent localized shrinkage porosity. When the molten alloy fits the heated casting ring, the pattern area should solidify first and then the reservoir last. Because of its large mass of alloy and position in the heat center of the ring, the reservoir remains molten to furnish liquid alloy into the mold as it solidifies. The refractory cast is attached to the base of the mold former using base plate wax. The top part of the mold is then attached and sealed using sticky wax. Colloidal silica special liquid for phosphate bonded investment is dispensed and then added to a clean dry mixing bowl. Then the powder is added to the liquid. Mixing is performed gently until all the powder has been wet. Otherwise, the unmixed powder may inadvertently be pushed out of the bowl. Mechanical mixing under vacuum removes air bubbles created during mixing and evacuates any potentially harmful gases produced by the chemical reaction of the high heat investment. A thin film of surfactant is applied on the pattern to reduce the surface tension of the wax and permit better wetting of the investment to ensure complete coverage of the intricate portions of the pattern. After mixing is completed, the pattern is now ready for investment. The ring is placed on a vibrating table and the investment material is allowed to flow slowly to cover the wax pattern and the sprue channels. Note that excessive vibration should be avoided because it can dislodge small patterns from the sprue former, resulting in miscast. Once the investment has set for appropriate period of time, approximately for 1 hour, it is then ready for burnout. The time and temperature required to eliminate wax from the mold cavity is specific to the refractory alloy system that is being used. Each system is developed to provide mold expansion that closely matches the anticipated shrinkage of the alloy as it solidifies. Since the ultimate fit of the restoration is dependent upon this relationship, the manufacturer's directions must be carefully followed. Burnout furnaces can either be electric or gas and must be vented to allow the escape of noxious fumes resulting from the process. Most modern furnaces permit electronic control of both time and temperature. Although insufficient burnout can result in technical problems such as incomplete casts and insufficient mold expansion, there is little that the clinician can do to influence laboratory management of these areas. Fortunately, most laboratories follow the manufacturer's recommendations. On the other hand, heating the mold beyond the intended range inevitably results in breakdown of the binder and destruction of the mold. Again, modern furnaces protect against these potential problems. Induction casting of removable partial denture frameworks is the method of choice. Removable partial denture alloys are cast in the temperature of 1371 Celsius range. Induction casting is based on the electric currents in the metal core induced from a magnetic field. A heating coil of copper tubing is shaped to fit closely around the casting crucible and is attached to an alternating current source. The alternating current in the coil sets up eddy currents of electrons in the crucible and the alloy. The movement of these currents melts the alloy. The heating coil, also at risk of melting during the heating cycle, is internally cooled by water. An electronic sensor directly above the crucible measures the temperature of the alloy throughout the heating process. This optical sensor activates the casting mechanism at the temperature selected by the operator. The placement of the alloy ingot into the uncontaminated crucible begins the casting sequence. Activation of the alternating current source starts the heating process. While the alloy is heating, the mold is removed from the furnace and placed in the casting arms holding mechanism. Once the metal has reached the casting temperature and the heated casting ring is in position, the machine is released and the spring triggers the rotational movement. As the metal fills the mold, a hydrostatic pressure gradient develops along the length of the casting. The pressure gradient from the tip of the casting to the bottom of the surface is quite sharp and parabolic in form. When the casting process is completed, the mold is removed from the casting machine and allowed to cool down according to the manufacturer's instructions. At the appropriate time, the outer layer of the refractory material is removed by tapping it with a mallet. The resulting investment is then removed by airborne particle abrasion in a self-contained machine manufactured for this purpose. Subsequently, the casting is examined for defects. If the casting is deemed satisfactory, finishing and fitting procedures are begun.